55 Cancri carries a nickname that could not be more misleading: the Diamond Planet. The name paints a picture of a glittering cosmic jewel, a sphere of pure sparkle waiting in the dark. The reality is a world of absolute nightmare, a place where the sky is a black void and the ground is a single global ocean of molten rock. The temperature here reaches 2,400 degrees Celsius, hot enough to melt metal in an instant and turn any fantasy of crystalline beauty into ash. It is so violently hot that it cannot even hold onto a proper atmosphere, yet a thin, strange veil of gas clings to its surface. So what made astronomers look at this hellish world and see a colossal diamond, and why were they so certain they were right? In August 2004, a team led by Barbara MacArthur at the McDonald Observatory in Texas was using the Hobby telescope to measure the wobble of a sun-like star called 55 Cancri A. They were looking for the telltale gravitational tugs of hidden planets, and what they found would eventually ignite a global sensation. The team detected a small rocky world, later identified as 55 Cancri E, a super-Earth and the first of its kind ever found orbiting a star similar to our own Sun. That discovery, published in the Astrophysical Journal, was remarkable, but it was just the beginning of a far stranger story. 8 years later, in 2012, a postdoctoral researcher at Yale University named Nikku Madhusudhan dropped a bombshell that would change the world's perception of this distant planet forever. He led a study, published in the Astrophysical Journal Letters, proposing that 55 Cancri E was composed primarily of carbon, with the startling possibility that as much as 1/3 of its mass could be pure diamond. To put that in perspective, that would be roughly 3 times the entire mass of the Earth, all in the form of a giant cosmic jewel. The media went into a frenzy, and almost overnight the planet was rebranded as the Diamond Planet, with headlines shouting about a celestial body worth an estimated $26.9 million. It was a narrative too perfect to resist, a story of unimaginable wealth floating in the darkness of space. But in the middle of this hype, a critical question seemed to get lost. Why would scientists believe that a world with a surface temperature of 2,400 degrees Celsius could be covered in diamonds? The answer, as it turns out, wasn't about the surface at all. The research team's calculations suggested that the immense pressure a few hundred kilometers beneath the scorching crust, reaching millions of bars, would be enough to compress carbon into diamond. This meant the treasure, if it existed, wasn't sparkling on the surface, but was buried deep within the planet's interior, hidden from any telescope that could ever hope to see it. The truth, it seemed, was a lot more complicated than the front-page headlines suggested. The initial discovery was an achievement, but the diamond rush was a different kind of event entirely. The story of 55 Cancri is a perfect example of how scientific nuance can be lost in the rush for a spectacular headline. So how can you avoid being misled by such cosmic rumors? First, always check the source. Information must come from peer-reviewed journals like Nature or the Astrophysical Journal, or from official space agencies like NASA or ESA, not from unverified aggregator sites. Second, always look for the publication date. Science moves fast, and the Diamond Planet story from 2012 was already being refined by newer data from the James Webb Space Telescope in 2023. But if the diamonds are hidden deep beneath the surface, what does the surface of this planet actually look like? To truly grasp why 55 Cancri is a world of relentless fire, you must first understand that it is tidally locked. This means the same hemisphere perpetually faces its star, while the other remains in an eternal frigid darkness, a division that creates a planet of extremes. Because it is so close to its sun, the gravitational pull has synchronized its rotation, locking one side in a permanent scorching day and the other in an unending night. On the day side, temperatures soar to a brutal 2,400 degrees Celsius, hot enough to melt rock into liquid. The night side, while still incredibly hot at over 1,000 degrees, is comparatively cooler, and this colossal difference in temperature acts like an engine. This extreme temperature gradient drives ferocious winds that whip across the entire planet, moving at supersonic speeds as the atmosphere desperately tries to equalize the immense heat. The night side is not cold, but a mere 1,000 degrees, which is still hot enough to keep the entire surface in a molten state. Now, the crucial evidence for this vision of a molten hell came from a landmark study published in the journal Nature in 2023. Scientists used the James Webb Space Telescope's MIRI instrument to measure the heat radiating from the planet, and what they found was stunning. The data showed a massive temperature difference between the day and night sides, far too large to be explained by a solid, rocky surface that would conduct heat evenly. A solid surface would retain and redistribute some of the star's energy to the night side, but the observations show the night side is much colder, which is only possible if the surface is a liquid. This finding was a powerful piece of evidence, pointing directly to a world covered in an ocean of molten rock, not a solid crust. This confirms a beautiful, terrifying story of a planetary surface that is never still. The constant churning of the magma, driven by the immense heat from its star and the immense pressure of its own gravity, creates a dynamic, ever-shifting landscape. And the clues for this churning had been there for a decade, as observations from NASA's Spitzer Space Telescope back in 2012 had already hinted at something extraordinary. Data from Spitzer showed that the hottest points on 55 Cancri E were not in the same place every time it was observed. They were moving around. These shifting bright spots were a mystery, but they hinted at a surface that wasn't static. Instead of a fixed, solid world, the planet showed signs of having giant hotspots that could drift across its surface, a phenomenon that precedes the more detailed observations of Webb. The story was solidified by a team at the University of Cambridge, led by Dr. Emily Sanford. They championed a technique called eclipse mapping to analyze 10 years of Spitzer data in a study published in Nature Astronomy in 2019. By meticulously studying the planet's light as it disappeared and reappeared behind its star, they created a 3D temperature map of its surface. This was the first time this technique, normally reserved for giant planets, had been used on a super-Earth, and it revealed a landscape more dynamic than anything we have on our own world. The map showed that the entire surface is a roiling, churning body of molten rock, a giant ocean of lava with giant waves and currents. It is not just a hot, rocky planet, it's a planet with its surface in constant motion, a state that is difficult to even visualize from our perspective. To check this for yourself, just look at the most recent scientific publications from the James Webb team, as the science is moving so fast. The discovery of this shifting surface is more than just a fascinating detail. It's a testament to how our picture of a planet can change with better data. Every observation from Spitzer and James Webb painted a picture of a world in constant upheaval, a dynamic, molten planet. The surface is not a solid place. It is a turbulent ocean of fire reshaping itself with every passing moment. This planet has no mountains, no valleys, no continents, just a global ocean of incandescent rock constantly churning from the immense forces acting upon it. It makes you wonder, if the surface is a churning sea of lava, what could its atmosphere possibly be like? The real puzzle begins with a paradox. A planet orbiting its star at a distance where the surface should be stripped bare, yet a thin veil of gas persists. This is the mystery of 55 Cancri E, a world so hot that it should have lost any atmosphere long ago, and yet observations tell us a different, far more surprising story. How can a planetary hellscape, with temperatures that melt rock, hold on to the very thing that should have boiled away into the void? The answer forces us to rethink what an atmosphere truly is, and where it can come from in the first place. The logic seems inescapable. With a dayside temperature of 2,400 degrees Celsius, the gas molecules should be moving at speeds fast enough to escape the planet's modest gravity, essentially bleeding the world dry over cosmic timescales. A planet that close to its star should be a barren, airless rock, a perfect vacuum wrapped around a lava ocean. Yet, when the James Webb Space Telescope turned its instruments toward this distant point of light, it found something that completely defied that expectation. The data, published in the journal Nature in 2023, revealed the unmistakable spectral fingerprints of carbon monoxide and carbon dioxide. The planet has an atmosphere, a thin one, but an atmosphere nonetheless. How is this even possible? The resolution to this contradiction lies in the very nature of the world itself. This is not a static ancient sky. This is a secondary atmosphere, one that is not a remnant from the planet's birth but a constantly produced veil, exhaled from the magma ocean below. The vast churning sea of molten rock acts as a planetary furnace, perpetually releasing volatile gases. The extreme heat drives convection within the magma, and these gases are continuously outgassed, replenishing the atmosphere as quickly as it is stripped away by the stellar wind. It is a dynamic equilibrium, a world actively creating its own sky. You might be surprised to learn that this isn't just a hypothetical model, as the team behind this finding was an international group of scientists from the University of Cambridge and NASA. Their work with the MIRI instrument on Webb in 2022 and 2023 was a monumental achievement. They captured the light from the planet as it passed in front of, and then behind, its host star, teasing out the faint signal of the atmosphere from the overwhelming glare of the star. It was the first time a secondary atmosphere was so strongly confirmed on a super-Earth, a rocky world significantly larger than our own. Let me show you how you can stand on the shoulders of this research. The first step is to go to the NASA Exoplanet Archive website, where you can find the data for thousands of confirmed worlds. Then simply type the planet's name, 55 CNCE, into the search bar to pull up its full list of parameters from mass and radius to orbital period and the original scientific papers. This discovery elevates 55 Cancri E to a special class of objects. For decades, the expectation has been that small, rocky planets orbiting so close to their stars would be airless worlds, their ancient atmospheres eroded by intense radiation and stellar winds. Finding one with a persistent, self-sustaining atmosphere is a profound shift. It suggests that a molten surface can be a powerful source of atmospheric gas, potentially implying that many other seemingly barren lava worlds might be wrapped in a similar, ever-renewing shroud. So, we've gone from a planet that should have no sky to one that is actively creating its own, a breathtaking act of planetary defiance. We should pause here for a moment, because this simply doesn't happen on Earth. Here, our atmosphere is a thin, precious layer that has been shaped by billions of years of biology. We don't see it being spewed out from the ground at a rate that matches our planet's escape. The mechanisms are completely different, which is why these observations are so valuable. They show us a fundamental process at work on a massive scale, a world continuously turning its own molten interior into a fragile sky. This single fact, that its very exoplanet is one of the first rocky worlds ever found with an atmosphere, a direct result of this process, marks a milestone in our quest to understand the diversity of worlds beyond our solar system. But if an atmosphere can be born from a lava ocean on such a scorched world, it makes you wonder what else could be hiding in that thick, glowing air. Somewhere in the swirling carbon haze of this tortured world, a beautiful idea was born, only to be crushed by the very physics that created it. The theory suggested that droplets of liquid diamond could condense in the atmosphere, falling like rain through the thick, scorching air, just as water rains on Earth. This was the dream that captured the world's imagination. Massive and a planet where the very skies poured out treasure. But a newer hypothesis from 2023 proposed a crucial detail that changed everything, suggesting this diamond rain is not a global phenomenon at all. It would be confined to a thin, razor-sharp boundary between the eternal day and the endless night, a place called the Terminator. Here, the sudden dramatic drop in temperature might just allow carbon vapor to cool enough and condense into glittering crystals. Yet, this is where the fantasy begins to shatter against the brutal facts of this infernal world. Have you ever wondered what it would truly be like to stand on a world where gemstones fall from the sky, only to realize you would never live to see them land? The climate models that gave life to this idea also carried its death sentence, showing that while these crystalline formations are theoretically possible, they are doomed the moment they begin their fall. The diamonds would evaporate long before they could ever touch the molten surface, because their melting point is around 3,500 degrees Celsius at standard pressure. This world is a furnace hot enough to turn the very symbol of permanence into a fleeting gaseous memory. To understand why, you have to picture the journey of a single carbon atom in this hostile environment. It is lifted high into the atmosphere by violent convection currents, where the temperatures cool just enough for it to solidify into a precious crystal. But as it gains mass, it begins its descent, falling back down towards the crushing heat of the magma ocean below. It is a one-way trip, a cycle that begins with immense hope and ends with absolute annihilation. The deeper it falls, the hotter it gets, until the structural integrity of the diamond itself gives way, its carbon bonds breaking apart into a cloud of vapor once more. This brutal process means that the diamond rain, if it does occur, is a phenomenon that can only be observed in theory, never witnessed on the surface. The real treasure, the diamonds that actually exist, are hidden far away from the spectacle of the skies, buried deep within the planet's tortured core. At depths of just a few hundred kilometers, the pressure becomes almost unimaginable, reaching millions of bars, a force powerful enough to squeeze carbon into the hardest natural substance known to us. That is where the real diamonds of this world are forged, not in the fleeting moments of a rainstorm, but in the crushing, eternal darkness of a molten heart. The idea that this planet is a giant glittering gemstone floating in space is the most beautiful lie astronomy has ever told us. It was a media sensation in 2012, when the planet was breathlessly declared to be worth $26.9 million, a figure so absurd it feels like a cosmic joke. But as the flashy headlines faded, the careful, unglamorous work of science began to reveal the truth. The detailed observations from Spitzer and later the James Webb Space Telescope painted a far more complex and violent picture, one not of a silent jewel, but of a churning, glowing cauldron of lava. This is the story of a myth being dismantled, not by a single catastrophic discovery, but by the slow, patient accumulation of better data. This is the lesson that makes this entire journey so valuable, reminding us that scientific understanding is not a fixed monument, but a living river that constantly changes its course. So, the next time you see a headline about a planet made of diamonds, remember that the reality is often far more fascinating than the fantasy. It is crucial to understand that diamond rain is not like the gentle rain we know. It is a phenomenon of carbon condensing into crystals and falling due to shifts in pressure and temperature. Also, you must distinguish between the kind that might occur on ice giants like Neptune under immense pressure and the theoretical one on carbon-rich planets like this. But if there are no diamonds falling on the surface, what exactly makes this planet so special that NASA would dedicate precious observing time to it, night after night? No planet has been studied more obsessively in the last 2 decades. The scientific literature on 55 Cancri is vast, with more than 50 peer-reviewed papers published since its discovery in 2004, according to the NASA Astrophysics Data System. That alone makes it one of the most intensely examined worlds beyond our solar system, but the numbers get even more striking. The NASA ADS index shows that over 300 scientific papers have cited its data, which puts it in an exclusive club of exoplanets that astronomers simply cannot stop thinking about. Why does this single world command such attention? Because it offers something no other known planet can. When the James Webb Space Telescope planned its first observing cycle, the list of targets was incredibly competitive, with scientists from around the world fighting for precious hours, and 55 Cancri E made the cut for that first cycle. That decision was not accidental. This planet was prioritized because it represents a natural laboratory for understanding a class of worlds we know almost nothing about, the hot, molten, rocky planets that orbit uncomfortably close to their stars. The team behind those observations, an international collaboration involving researchers from the University of Cambridge and NASA, spent hundreds of hours staring at this one tiny point of light, and the technical sophistication they brought to the task is staggering. The methods they used to read this distant world sound almost like magic. One technique, called transmission spectroscopy, works by catching the starlight that filters through the planet's thin atmosphere and breaking it apart into its component colors, revealing which gases are present by the fingerprints they leave in the spectrum. This is how we learned that its atmosphere contains carbon monoxide and carbon dioxide, and it is the same technique that has turned the James Webb Space Telescope into the most powerful tool we have for studying distant worlds. But the most remarkable achievement came from a different method entirely. A team at the University of Cambridge, led by Dr. Emily Sanford, developed a way to map the temperature of the planet's surface in 3 dimensions using data from the Spitzer Space Telescope, a technique called eclipse mapping that was previously reserved for giant planets. They watched as the planet moved behind its star, and by measuring the tiny dips in light, they could reconstruct where the hot regions were located on its surface. This was the first time anyone had applied eclipse mapping to a super-Earth, and the results were breathtaking. The map showed that the hottest spots were not where you would expect them to be, shifted away from the point directly facing the star, which suggested something extraordinary about how heat moves across the planet's surface. You can see why scientists keep coming back to this world. It is not just one discovery that makes 55 Cancri special, it is the way every new observation forces a revision of what we thought we knew. If you want to see this for yourself, you can visit the NASA Exoplanet Archive and use the advanced filters to compare this planet against other super-Earths, watching how it stands out in the distribution plots. Then scroll down to the publications section and you will find the complete list of every scientific paper written about it, each one a new chapter in a story that keeps evolving. That archive is the same tool professional astronomers use every day, and it will show you exactly why this small, dark, hellish world has become the most hunted planet in the sky. The more we study 55 Cancri E, the more we realize it is not a strange anomaly, but a key that could unlock the secrets of an entire class of planets we have only just begun to discover. Every observation brings us closer to understanding what happens when a rocky planet forms too close to its star. And that understanding could one day help us recognize which distant worlds might be worth a closer look. But to truly grasp why this planet matters, we need to step back and consider where it came from, and what the story of its ancient star system can tell us about our own place in the universe. To understand this planet properly, you have to step back and look at the entire system it calls home. 55 Cancri E is just one of 5 planets orbiting a yellow dwarf star named 55 Cancri A star so similar to our Sun that you can actually see it with the naked eye on a clear night. This system is ancient, and its history is etched into everything we observe today. It was actually one of the very first multi-planet systems ever discovered, with the first planet, 55 Cancri B, found back in 1996, a discovery that fundamentally changed how astronomers thought about planetary architecture. But the real mind-bender is the age. The parent star is estimated to be about 10.2 billion years old, which is more than twice the age of our Sun at roughly 4.6 billion years. Think about that for a second. This means 55 Cancri E didn't form recently. It emerged when the universe was only about 3.6 billion years old. It is a fossil from a time before Earth even existed, and it has been silently orbiting its star for over 10 billion years. That is longer than the entire history of life on our own planet. A span that makes the dinosaurs look like a fleeting moment. To put it in perspective, our Sun and Earth took about 4.5 billion years to produce intelligent life, and even then, it happened at the very last possible moment in our Sun's life. Meanwhile, this world has endured 10 billion years of scorching radiation and tidal locking, a hellish eternity without ever producing anything close to a single microbe. And the proximity is staggering, with 55 Cancri e orbiting at a distance of just 0.1544 astronomical units from its stars, which is roughly 65 times closer than Earth to the Sun. The sky there must be a spectacular, terrifying sight, a burning orange and yellow glow that fills the entire view, a permanent reminder of the furnace it circles. Now, this is the key thing to understand about diamonds here on Earth. They don't form on the surface where we find them. They form deep below, around 150 to 200 kilometers down, under immense pressure of about 45 to 60 kilobars. If you compare that to 55 Cancri e, you have to grasp that any diamonds on that world, if they exist, would have to be deep in the core, where the pressure is millions of bars, because the surface is simply too hot at 2,400 degrees Celsius for solid diamond to survive. The conditions are so radically different that you can't just transplant terrestrial logic to an alien world. It is a place where the very atoms are crushed into forms we can barely imagine. The carbon that could make those mythical diamonds is there, but it's locked away under a hellish crust of molten rock, never to see the light of its dying star. So you begin to realize that this planet is not a treasure chest, it is a cosmic gravestone. And that is why this world is so profound. Its 10 billion years of struggle against the void illuminate our own fragile luck. We exist because our planet was gentle, because we weren't locked to a star that fried us, because we had oceans instead of lava, because we had time. 55 Cancri e, in its harshness, shows us just how improbable our own existence really is. The story of 55 Cancri e isn't over, it's being rewritten by new eyes in the sky. So the diamond planet does exist after all. We just had the wrong picture in our heads. What we imagined as a glistening jewel floating in the black is actually a churning world of molten rock, locked tight to its star, its surface a seething ocean that never rests. It is a strange, harsh beauty, but a beauty nonetheless. The story of 55 Cancri e is a story about how science corrects itself. In 2012, the headlines roared with the promise of unimaginable wealth, but it took the more careful eyes of the James Webb Space Telescope in 2023 to show us the truth, a truth more interesting than any science fiction. The universe, it turns out, is more inventive than our dreams. Consider the comet 67P, studied by the Rosetta mission, a frozen world whose surface sits at a frigid -43 degrees Celsius, forever locked in a deep freeze. The contrast is staggering, a universe of fire and ice, with our own planet somewhere in between. Our Milky Way alone hosts something like 100 to 400 billion stars, and current data suggests that most of them have at least one planet. That means hundreds of billions of worlds, each with its own unique drama unfolding. Among that incomprehensible number, we find a planet of lava and a comet of ice, and yet here we are on a world of liquid water and blue skies. A place that seems against all odds to have found the perfect recipe. So was 55 Cancri a disappointment, or is it a reminder that the truth, however strange, is always more valuable than the myth?